עידן, זה בסדר מבחינתך שמקליטים, כן?
פה.
מה?
לא רק שזה בסדר, אני מעלה את זה אחרי זה לערוץ יוטיוב שלי.
אוקיי. לא תיקנתי את העברית, אבל יש שגיאות עברית.
איפה יש שגיאות עברית?
אני חושב שאין בעברית המילה גדילה.
אוקיי, אבל אין, המצגת היא באנגלית, אין שם מילה אחת בעברית. אולי
לא,
באפסק?
באפסק ששלחת.
טוב, צר לי על זה, בסדר, מתנצל.
טוב, אז נתחיל. So I am very happy to host today Idan Tobis. This is his thesis on the master's degree. And the talk is about rectified logarithmic activation function for neural network. And I hope that many other students will take it and come and give a talk on their work. Like Idan is doing it, I think, the second time already. Okay, Idan.
Okay, so thank you everybody for joining. My name is Idan Tobis. Most of you know me. Those who don't, two words about me. I did my BSc in engineering at the Technion somewhere in the last millennium. I did a micromasters at statistics and data science at MIT without a thesis, and I'm currently working on my second master's here at the HIT with under the guidance of Professor Amir Averbuch, our distinguished host in this case. So today I'm going to present the thesis I'm working on. This is a work in progress. So it is about what I call ReLog, or a rectified logarithmic activation function for neural networks. And just a reminder, the role of activation functions. Activation functions are a crucial component in the success of deep neural networks. What they do is they introduce nonlinearity into what would otherwise be a linear model. Everything is just matrix multiplication. But once we multiply the inputs and summarize them, we need to add nonlinearity, and that's the role of the activation functions. Otherwise, everything collapses into a single linear transformation, because if you have a series of matrix multiplications, they just collapse into a single matrix multiplication. So eventually we have the activation function at the end determines how the neural network learns how to represent information in feature space, and how it is able to model complex behavior. Now, there is
Idan,
yes.
I suggest that you go one slide back and explain to people exactly where is the activation located.
Okay.
Because this is very crucial.
Okay, so let me go. So the single neuron layer, or single neuron actually, this is a neuron, then it is supposed to mimic the activity of the biological neuron. So instead of dendrites, we have inputs, and we multiply these inputs by weights. The weights are learned by the neural network, and then we summarize all the multiplication. We add bias, and then these results go through the activation function. Basically, the activation function tells us adds the nonlinear function on top of the linear matrix multiplication. Okay, so the output is basically just f, which is the function, the activation function, over the sum of all neurons. Okay?
Yeah, perfect.
Okay, so as I mentioned, all we have to do, the activation functions, what we usually want is them to be monotonous, meaning they go only one way. We would like to have them continuous and also, if possible, differentiable on all places. Some of them maybe like ReLU have a single point of non-differentiability at 0. That's usually not a real issue. And we have a plethora of activation functions starting from sigmoid and hyperbolic tangent, which are the classic activation functions, going through ReLU, which is the let's say the king of activation functions today, and more modern ones like Swish or ReLU, which are used for generative neural networks.
Idan,
Yes.
Idan, can you go back? Can you describe few? No, not here. Like to the activation functions.
Yes.
First, can you give us like some motivation how people invented? This is actually related to your talk. How people invented this like activation function, in particular, why
Yes.
sometimes I see the activation function they change in range and change in pattern. Sometimes it is between 0 and 1, sometimes between -1
Okay.
and 1, sometimes it go to infinity. I
That's
mean, you
I
can
will
just
go.
play and produce
Yes.
any activation function, or does it need to mathematically to fulfill certain rules, like for instance, convergence of the neural network or whatever. So, okay, this is for you.
So yes, I will go through it more thoroughly. I have a few slides later. I'm going exactly through those points of convergence in infinity. But let's for instance compare sigmoid to hyperbolic tangent. Okay, so sigmoid goes to 0 at minus infinity and goes to 1 at infinity. And basically, this came from you said what is the motivation? So this comes from probability theory, where you compress the entire axis from negative infinity to infinity to a number between 0 and 1, which is basically your probability. So this is a probabilistic function. It compresses the axis into a probability of, let's say, a certain feature existing or not existing, or a certain classification of an image being correct or not correct. Okay, so sigmoid originally the two main activation functions which were used until 2010 were again sigmoid and the hyperbolic tangent. Hyperbolic tangent is basically sigmoid times 2 minus 1. So it goes from -1 to 1 at -1 at negative infinity to 1 at infinity. So instead of saying we have a lack of a feature and the certainty of that feature, we have the feature and the negative of that feature. So those were basically the two classic activation functions. In 2010, LeCun and Benjo offered the ReLU. ReLU basically means that, and again, I will go through it later, but it's the maximum of 0 and z, okay? So if z is negative, it is 0. If z is positive, it's just z. So basically, it goes to infinity at infinity and to 0 at negative infinity, okay? So this means basically, if you look at it in the same kind of intuition, so a negative number means lack of a feature, and a positive number means a feature that grows as much as the result grows. And I will go through it in more detail in a few. The idea, the intuition behind it, I will go through it in a few slides, if you will. The only thing I would say is that people understood that when you have ReLU, when you have the negative part, it will lead to what we call dead neurons. So people introduced what's called the leaky ReLU, which means that we do have basically two linear functions, but on the negative side, the gradient is lower. Okay, so it will be alpha times z instead of z, and alpha is smaller than 1. Okay.
Just to add to what you're saying, Idan, and to Gadi's question, some algorithms differ different between the loss functions they use. So they may use the loss function takes the activation function into consideration, and based on different activation functions, you get at the end a different learning model.
True. Thank you.
Also,
Thank you,
you forgot, Idan, that all these functions need to be differentiable. This is very
Yes.
important for the learning. So,
And unless on us, let's say on certain point, like ReLU is non-differentiable here, and on certain point you can have a non-differentiable at a limited number of points. I agree. And I will use that. I will use that exact property. So the current king in let's say in general tasks is ReLU, and the main reason is that it's simple and computationally fast. Again, this was proven by Benjo and LeCun in 2010. This solves the problem of vanishing gradients that we have in sigmoid, where when you're far from the y-axis, your gradients basically vanish. So ReLU has always a gradient of 1 for positive inputs. And what it does, and this is again what Benjo and LeCun shown, is that it induces sparse activation, so it's also fast to calculate. So there's no surprise that this became the de facto standard for deep learning neural networks in let's call it in general tasks. Let's talk about generative tasks later, but in general tasks. So what's the problem? What's the problem with that? So I'd like to start with this image. It's a paraphrase on the Michelangelo's creation of man, creation of Adam. So I've asked Copilot to create a similar image, but where man creates AI. So can you see the problem here? Anybody sees the problem with this image? While the human hand is okay, the AI's hand has 6 digits, and this is not something surprising, I'm sure, to many of you. Because I've seen many of these artifacts coming when you try to ask AI to do an image. A lot of times you'll get these artifacts. So this brings us to the main problem with ReLU, and that would be its unbounded linear growth. So ReLU's gradient is constant for all positive x, and of course it's 0 for negative x. This means that the network gives equal importance to small changes regardless of the original output. So if we have an output of 1 and this changes to 2, this would be what we call a primary signal. It gives us the same importance as if the change is from 100 to 101. Okay? So the problem with that is that this may also overemphasize fine-grained detail in feature representation, which means, for instance, 6 digits instead of 5 digits. And we've all seen that when you create an image with AI, they hate empty spaces. They try to fill every empty space with something, with some kind of feature, and especially if it's diffusion models. So you get a very rich, too rich image, which distracts from the main focus of what you're trying to convey. So our hypothesis is that in generative tasks, this would be detrimental, okay? Because this leads to common artifacts, again, such as those extra fingers, extra hands, distorted textures, duplicated objects, and so on and so forth. So most of you do speak Hebrew, and most of you know the proverb "Kula Mosif Gorea." Talmud Bavli. And in English, it would be all who add detract. And this suggests that adding unnecessary detail detracts from the whole. So ReLU's principle is the opposite. It would go with the proverb "Kol hamarbe harei ze meshubach" from Pesach. Okay, "Kol hamarbe lesaper b'yetziat Mitzrayim harei ze meshubach." So what it does, it adds more and more late stage artifacts with no limit, and those late stage artifacts or those late additions cause those artifacts that detract from the quality of the final image. So what we need is an activation that follows the original proverb, all who add detract. What we want, the principle that we want to add is the principle of diminishing returns. So what we would like is a sublinear activation function that encodes a natural diminishing returns behavior. So in this case, a sublinear activation functions will have small changes at the start or close to the y-axis cause a strong reaction, but the further we increase the output, those small changes yield a smaller and smaller return, a diminishing return. So this introduces ReLog. So we want an activation function that models diminishing return. So it has sublinear growth, but we want it to stay fast. So the obvious answer to that would be a logarithmic function. Of course, we would like to add 1 to our output because, or to the input in this case, because we don't want to go to negative infinity. We want 0 to stay 0. However, we want to rectify it to keep it fast. So instead of using the original logarithmic function, we want to rectify it into a series of piecewise linear functions with diminishing returns. Okay? Now, of course, this adds the non-linearity on some points, but as we've seen, this is usually not a problem. So let's mathematically define it. First, we introduce an auxiliary variable that would be k, and that would be the floor of log on the base of 2 to x plus 1. Of course, if x is more than 0, if x is negative, then we just want to return 0, as in this case. Okay, now this would be a piecewise function where x is negative, of course, we return 0, and where x is positive, we return x plus 1 divided by 2 to the power of k. Again, k is the floor of the logarithmic of x plus 1, plus k minus 1. Why k minus 1? Because this would be basically the integral of the previous section of the previous triangle. Okay. So now we have our function is continuous, it's monotonous, and it has sublinear growth. Let's compare, and this I think answers your previous question, Gadi. So if we compare our function ReLog with ReLU, that's the orange graph, and sigmoid, that's the green graph, what we're seeing is that basically when we go to infinity, sigmoid goes to 1, and the gradients are vanishing. Okay, the gradients become 0, which further requires normalization, which in itself is a problem. I won't go into that now. ReLU, the yellow or orange graph, grows linearly without any bounds. So this could cause exploding activations. Okay, the opposite of vanishing gradients. Sorry, exploding gradients, not exploding activations. And ReLog in the middle is the middle path. So it grows, so it doesn't have vanishing gradients, but it grows unbounded, but it grows in a sublinear rate, so there are no exploding gradients either. Okay, so it's basically the middle path, or what we call in Hebrew shvil hazahav, the golden road between those two activation functions. So what's the problem with ReLog? So how do we compute K without an expensive log operation? We know that the log operation is very expensive, and especially for GPUs, because GPUs know how to calculate additions and multiplications. They're very bad with transcendental functions. Okay, so the solution is bitwise operations. What we're doing is we're leveraging the IEEE 754 standard, which is basically how we represent floating point numbers in the computer. And the way that we store them is that the exponent of the floating point number is actually the low precision logarithm, which is exactly what we want. So basically, we can do the implementation using only bitwise operations on the floating point representation. So first we have to convert them to integer representation and then do the math there. There is a problem with most languages. They do not allow us to do this. We cannot do it in Python. We cannot do it in C. We have to go to assembly in order to do that. So let's look at the algorithm. Basically, what I want to do, of course, if x is negative, I return 0. Otherwise, I add 1 to x, I call that z, and then I do a decomposition using IEEE 754 into the exponent and the mantissa. And all I have to do now is return the exponent plus the mantissa minus 1. And why is that? If we look at again, the representation, z equals mantissa times 2 to the power of the exponent. And again, in IEEE 754, the mantissa is between 1 and 2. So what we're doing is, since we have m plus e minus 1, or e plus m minus 1, this is equivalent to x plus 1 divided by 2 to the power of k, plus k minus 1, which is exactly what we want. Okay? So let's, again, I was not able to do that in C because basically C does not allow you to convert a floating, or to look at floating point representations as if they were integers. So I needed to go back maybe 25 or something years back to try to remember how to do these things in assembly, but eventually the code looks like this. So we're doing 2 steps. The first step is to find k. Basically, k is found when you do the end command with the first 8 bits being 1. So basically, again, in this representation, the first 20, the least significant 23 bits are the mantissa, and the last 8 are the exponent. And of course, we have a 1 for sign. So first we isolate the exponent bits, then we shift them to the right 23 places, and then we subtract the bias. Again, in this representation, you have a bias of 127. So this gives us basically k. Okay, now k, we save that because we will need that for the backpropagation step. Okay, so we save that. And now we're doing the second step where we just calculate, we shift back k 23 times, and we just add it, we just subtract the original number, subtract k from the original number. So basically that gives us 2 to the power of minus k. Okay. Now all we have to do is bring everything back to a single number, and that would be EAX now in this register. Okay. So again, step 1, we find k. And step 2, we perform the division by subtracting k from the exponent field of the float. Now, the main advantage is that we don't need the floating point unit to work. We don't need the logarithmic function, which is very costly. We don't need division, which is very costly. These things stop GPUs on their tracks. Everything else is just shifts and subtracts of bits. Okay, so this is very simple. This is very fast. Again, in theory, let's see how let's see if this is really true in our experiments. Now, we also in neural networks we need backward pass. So the backward pass is even simpler because we already have k because we saved k. So we can just create a new number 2 to the power of minus k. Okay, a very fast operation, and we don't need x, we don't need anything. We just either return 0 or 2 to the power of minus k. Okay, so that would be the derivative, and the crucial insight is that we don't need the original x. We just need to save k, and we already did that on the forward pass. So that would be the pseudocode. We already saved k, so we get that from memory, and we calculate the efficient power 2. Again, this can be done with bits, with integers, to the power of 2 to the minus k, and everything wherever k is negative, we mask it, and that's what we return. Okay. So again, this is simply one context lookup, one fast bitwise operation, and one multiplication. Very fast. So this brings us to the next question. Is it so? Okay, so we've seen that it's fast theoretically, but is it also theoretically sound? Meaning, can a neural network with a ReLog activation function as a universal approximation? Okay, so that would be UAT, universal approximation theorem. So again, I will not go through the entire rigorous proof. I will just give a proof sketch. So it was already shown that if you have a function which is continuous and non-polynomial, which is in our case, this is the ReLog is continuous and non-polynomial, then what we are doing is we're shifting ReLog units to produce localized bump-like functions, and those bump functions are then combined to approximate any continuous function to arbitrary precision. So again, this is just a sketch, but this establishes at least the theoretical soundness of ReLog as an activation function. But theory aside, let's try to do some experiments. So the first experiments we did, we tried to evaluate the approximation of a diverse set of deterministic functions. And we did that with a very simple multi-layer perceptron, or MLP, with 3 fully connected hidden layers and 256 neurons per layer. And the method was to use the exact same architectures with our function ReLog versus ReLU versus sigmoid, and then do 29 independent runs to get the statistics, and then compare the results in terms of, because this is regression, we used MSE, mean square error, with compared to the function, to the original function, to get the result. So what you can see is that for all, these are the first 6 questions. So first 6 functions. So we had a quadratic function, a cubic function, a sine function, a combination of sinuses, sawtooth function, square wave, and piecewise, Weierstrass, and logistic. These are, let's say, the continuous functions, and the last 3 ones are non-continuous, or at least non-differentiable: piecewise, Weierstrass, and logistic map. And as you can see, the blue graph is ReLog, and the green one is sigmoid, and the yellow one is ReLU. And in all cases, in all functions, ReLog had a much better, meaning it's much more skewed to the left results. The mean is much lower. The mean of the loss is much lower. And also the variance is much lower as well. Okay, because as you can see, other than in sawtooth, where the sigmoid for some reason had a smaller variance, the variance of ReLog was much lower in all cases. This is especially pronounced in the non-continuous functions like piecewise, Weierstrass, and logistic map. And these are the graphs, but let's look at the numbers. So we can see that in all cases, the MSE in ReLog was much lower than that of ReLU and sigmoid. In some cases, by a lot, I don't know, 10 to the by tens or hundreds or even thousands. And if we compute this statistical significance, then in 17 cases out of 18, because we have 9 functions times 2, because we have ReLU and sigmoid, in 17 out of 18 cases, it was also statistically significant compared both to ReLU and sigmoid. In one case, in the sine function, it was still better, but not statistically significant, this one, okay? 0.08 instead of 0.05. So the first finding we have on our first experiment is that ReLog consistently outperformed both ReLU and sigmoid in terms of validation MSE. This is a regression. And the second finding is that the advantage was particularly pronounced for nonlinear and chaotic functions, such as the cubic function, the logistic map, and the Weierstrass series. And the third finding again is that those improvements were statistically significant in 17 out of 18 comparisons. The fourth finding, which is maybe not that related to our function, is that sigmoid collapsed entirely on the sinusoidal and square wave function tasks. So the conclusion here is that ReLog is not just a universal approximator in theory, it is also a better and more robust approximator in practice. The second experiment we did was a classification task. We did the classic CIFAR10. CIFAR10 is just a very simple 10 class images of dogs, cats, fish, people, and so on and so forth. 10 classes of images, and we need to classify those images. It's a very classic task that we know that convolutional neural networks do very well. So we used a very simple convolutional neural network with, and then again, we used a drop-in. These tasks are, again, this is where ReLU is really the king. So we wanted to see if we can drop in ReLog instead of ReLU in a standard CNN, in a standard convolutional neural network. And the setup is a medium-scale convolutional neural network on the CIFAR classification task. Again, very standard. We trained it end-to-end. It doesn't take a lot of time. And the only variation was the activation function between ReLU and ReLog and the sigmoid. Sigmoid doesn't work very well on that task. And then again, the classification LMP, we used only ReLU. We did not use ReLog. Now, we repeated that for 5 independent runs to get some statistics. And what we found is that ReLog, even though it outperformed ReLU, it was not statistically significant. So we can see the results. The median is better. The overall result is better, but it is not statistically significant. The P we got was over 0.2. So I cannot say that this is actually statistically significant than ReLU, but it is a safe replacement. Not a better replacement, but a safe replacement. The third experiment we did was to find the, is it really faster than ReLU on the computer, in real life? And so we compared some of the, let's say, some of the known activation functions like swish and ReLU, together with the classical one, sigmoid, hyperbolic tangent, and ReLU, and also the norm, let's say the regular, the normal log2, just for comparison, because we know that log2 is slow. So we've seen that the piecewise approximation of the logarithm, which is the blue graph, is much faster than everything else, including even ReLU. Now I have a suspicion that this is because maybe ReLU is implemented in C rather than assembly, and again, we implemented ReLog in assembly for the obvious reasons that C would not allow us to do so. But other than that, it was even faster than ReLU. Again, we ran 4 million calculations of these activation functions to get reliable results. So the finding is that ReLog is the fastest activation, even faster than ReLU. Okay. The conclusion we have is that the bitwise implementation is not just cheap; it is significantly faster than the industry standard ReLU, making it ideal for edge devices. This would be again, this would be a very small difference if you're running this on a GPU or on a CPU for training. But when you're inferencing on an edge device, let's say you have a quadcopter or some robot, and you have and your CPU is not that strong, this would lead to every microsecond count. So this would be important for edge devices. So to summarize the contributions, first of all, we proposed ReLog, which is a novel sublinear activation encoding for diminishing returns. This is hardware friendly because it's efficient both forward and backward passes, and it only uses bitwise operation, nothing more. It's theoretically sound. We've proven UAT theory. It's empirically validated, so it is a better approximator than ReLU and sigmoid for regression tasks, and it's a safe drop-in, even though it's not better, not significantly better than ReLU in classification tasks. And it is faster. Now I have to remind you that this is a work in progress. So we still need to conduct the following experiments. So the first one is to show that this is safe to replace ReLU with in transformer fast-forward network layers, such as SST task. We want to work in speech. Because as you know, right now, generative speech, at least to my ears, because this is this is what I did in industry, sounds awful. So I would like to test it in speech to replace ReLog, ReLU with ReLog on speech. And then the critical test is to use diffusion with to replace the standard ReLU or swish with ReLog and see if we can reduce the number of artifacts in generative tasks like diffusion. Okay, so this would close the loop because this would prove or disprove the theory that the diminishing returns will solve the problem of artifacts, of generative artifacts as we know them, such as extra fingers, extra hands, and extra information in the background. Okay. So the experiment that is running now is replacing the ReLU or swish with a ReLog in a tiny unit for diffusion model, and the goal is to measure the Frechet inception distance, the diversity, and then to perform qualitative analysis of the artifacts to see how many fingers, if we can reduce the number of fingers and extra fingers and extra hands in our images and other artifacts as well. This would be the key test of the core hypothesis of the diminishing return hypothesis that we conducted. So thank you for your attention to this matter. I would be more than happy to answer any questions, Gadi, or anybody else. Yes,
Gadi, what about you, Gadi?
Gadi, you're muted. You're-
No, actually, I'm now driving, so I'm very impressed. Actually, I really think it has a lot of potential. I do think, like for scientifically, I'm curious if you can make actually like design criterion for activation function that actually you will not need even like to do any running of simulation, but just from you can incorporate like all the knowledge that you think that a good activation function need to fulfill. You need to incorporate it into the design criteria of activation function. I think this by itself can be a nice contribution, because you kind of, what you said was more like a kind of intuition or kind of, but you didn't like make a precise mathematical constraints. I think if you do it, you can push further, even without simulating your algorithm. You can push it forward. Yes, just if you show that if you use the proper design criterion for activation function, and that your specific activation function actually is like optimal solution to this design criteria, then I think it will be like a great contribution to the field. If you need my help for this, I can assist you for sure.
Thank you, Gadi.
One additional comment, Idan. I think one of the problems in text and RNNs is the diminishing returns, diminishing gradients. And I think it might be, before going to the transformers, I didn't see that you mentioned to try it on RNNs as well, but I think it might be interesting to check that as an alternative to the more complex transformers at some point, and see if how they handle these type of problems.
But so you mean compare LSTMs, for instance, with transformers, or compare LSTMs with ReLU or LSTMs work with sigmoids and hyperbolic tangent. So you're saying, if I understand correctly, replace those with ReLogs and then try that.
Exactly.
That to that's an interesting thought. I might let me write that down. That sounds like very interesting. Thank you. Okay, so I'm writing down Gadi's what Gadi said, which is to try to do some more mathematical theory, and so we don't have to do the actual experiments. And then
No, you don't. It does not eliminate the need for.
Okay.
But the experiment will be just for validation. Yes, but for you make it just much stronger. And actually, you can incorporate, like, you know that one of the problem is vanishing gradient, so you can incorporate into the design criteria that a term that actually speaks about it punish you when you have like more vanishing gradient, etc., etc. So you know, it is very creative task. If you need help, I can assist you.
Okay. Okay.
More questions?
Thank you both. That was very helpful.
Thank you. First of all, thank you very much for a very, very interesting presentation. I have the question from the different side. Actually, I worked, and now one of the papers I submitted already accepted, which is the paper where I show how to transform neural networks to the threshold functions network. And two ways, from this to that. And it is just learning activity for students. It is fine, no problem with that. But my question is like that. In my research, it's traditional artificial intelligence, traditional neural networks, I have threshold function. When I'm moving to the activation function you talking about, as far as I have a feeling, as far as I understand, actually it is moving to the modern system like generative AI. So my question, what do you think about this direction? If, for example, to try to teach student classical threshold functions, and which is absolutely clean and classical, and but moving from different kinds of activation functions you show, it is a way to go to latent space, to the space where have a sensitivity to context and all this stuff, which is actually the new direction, new way. It is our dream. Do you think it is have a potential, this kind of approach?
Yes, I do think so, very much so, because what you're saying is let's take the threshold function
Absolutely.
and let's and use our function instead. It's to use that as an educational tool. Yes, I think that this might be a very interesting idea, a very good idea.
Yeah, because when they are working with classical threshold, it's very nice. It's not easy to transform. I work with students, they're happy about their success, everything is excellent. But when we are moving to your direction, is make this direction of research and studies is absolutely another level. So I believe that is good.
So if you look at, so for instance, if you look at the gradient of the ReLog function, this would be something like this, right?
Correct.
So it will be a stepwise function like this.
Absolutely.
So it would be more intuitive maybe for the students to understand it.
Kind of a connection, let's say, between discrete and analog, maybe even indexical. We call it indexical, but indexical is kind of difficult term. But we're just talking about moving from clean digital, and so how to explain the success of generative AI. I think it's good direction.
I completely agree. Thank you. I will write this down as well.
Thank you.
Any additional questions? Okay, thank you for those who, again, so thank you everybody for attending, and thank you for for your attention, everybody, and that's it basically. If you have any additional, Amir, if you have additional things you want to say, maybe.
No, I think it was excellent talk, and I hope that other students will follow you and come and present their stuff.
Thank you so much. That's really heartwarming coming from you.
Okay, thank you everyone, and see you next week.
See you next
Great
week.
talk, Idan. Thanks.
Bye-bye.
Thank you very much. Bye-bye.
Thanks. Bye.
Bye.